Now I'm going to talk about the post-development. We're going to talk about the curve number and the time and concentration. Everything else, the precipitation, the drainage basins will change. The hydraulic group, soil group won't change. Curve number will change. Time of concentration will change. Runoff and the peak discharge will change. So this is going to be our project. So what we have is a road coming in, going down into a cul-de-sac. Another road coming through. Now everything that has the dark dashed lines is the drainage basin. I went ahead and delineated it. All the water in this side of the basin, the road is split in half because it is a crowned road section. That means all the water, and I will give you these drawings so you can look at them, all the water goes to this inlet on this side. All the water over here goes to the inlet on this side. All the water that's in here goes to an inlet here in the street. All the water on this side goes into an inlet on that side of the street. There is a catch basin at this end, so the water drains down to this point. Now, all of these pipes discharge to this pond. Okay, so what we're going to be looking at this semester is we're going to size this pond, make sure it's sized the proper size. If not, then we might lose a couple lots to put the pond bigger. It won't probably go smaller. It will also design the size the pipes need to be to hold all of this water. Again, there's 5.47 acres totally, but now we have to figure out what the acreage is in each one of these because these inlets can only hold so much, and this discharge point can only be, or the discharge point in the water, the pond can only hold so much depending on the depth. Okay, so what we need to do is we need to figure out area of each one of these. We'll have to figure out our curve number, our time of concentration. Now the soils group isn't going to change, so we don't have to re-look up the hydrologic soil group. Our time of concentration for each one of these points is going to be different. When we're first looking at it, we don't look at it individually. We'll look at time of concentration. What's the longest time of concentration to get to this pond? The pond gets designed first, and then the pipes get designed because of that tailwater effect. When water goes into the pond, it's going to stage back up into these pipes, okay? And if the pond stage discharges out to another place, it might have tailwater. For the time of concentration, we'll look at the longest flow path. So the highest point is going to be over here. It's going to roll down the lot. It's going to roll down the street, roll down the street, roll down the street, get into this inlet. So from here to here is going to be overland. Sheet flow, and then it's going to be shallow concentrated flow all the way through the curve. So these lines right here is the roadway. So it's going to have shallow concentrated flow all the way down to the inlet. Once it gets to the inlet, it's going to go through channel flow. It's going to be piped. All right, so we have to figure out time of concentrations there. That's the time of concentration that we'll use for the pond design. We'll have to look at time of concentrations individually of each basin for the pipe design, but that'll be later on in the course. Right now, we're just interested in the pond design and how much flow is going to it. So we have our points of interest. Our points of interest for the beginning is going to be this point right here, discharging into this pond and then discharging off-site. I'll probably put a control structure, we'll talk about that in a bit, out to the west side of the project. Okay? That's where our point of analysis is. If we're looking at the storm, we have to look at each inlet. Our soil's not going to change. It's going to be a type A soil. The land cover does change, okay? Because now we're a subdivision. We actually have house and residential. Time of concentration, we just talked about that a little bit. We'll talk about it a little bit more. And then we'll have the solving of our initial abstractions, our Q runoff in inches and acres, in acre inches, and then our peak discharge in CFS. So for the post-development, we're going to actually talk about having residential development, about 1/8 of an acre. So if you look at the table 22-2A in the TR55 model, you'll actually come over here and you'll say, okay, here's residential, 1/8 of an acre or less, townhomes, 1/4 of an acre, I can't read what that says. A third of it. I'm too close to the screen. A third of the acre, a half acre. We know that it's going to be type A. Now, depending on the average percent impervious, and there is a table that says if you're going to use that at whatever percent impervious that is, then you can use that value. What I would like to do is create an Excel sheet that allows me to break down the area based on building size, which will be impervious, road, impervious, driveway, impervious, and then the rest of it's going to be locked and it'll be pervious. So I'm going to, instead of just using a default value, I actually might break it down. We'll take a look at that in the homework assignment. But for right now, just as an expression of talking, we're going to assume 1/8 of an acre, and we're going to come over here to the A value and see what the curve number is. Now, we also have the time of concentration, like I said. So same process. Now, the Manning's Inn that we use for this is going to be grass cover dense, because we're assuming Bahia, not Bahia, St. Augustine, which is really cushy. Bahia is like more your short prairie grass. So if it's Bahia, we have dense grass, so the Manning's Inn is going to be 0.24. Same thing. When we look at the shallow concentrated flow, when it becomes shallow concentrated flow, it's going to be in the roadway. So if it's in the roadway, I'm going to use the paved line, not the unpaved line. Part of that could actually be still in the lot, depends on how deep the lots are, but right now I'm thinking that it's all in the roadway. Once it gets past the roadway and gets into that inlet, we're actually going to use a pipe design. So we're going to assume that it flows, again, we're going to use the mean depth, the area of the pipe divided by the top, and we'll take a look at the mean depth of that, or at least flowing full. And we'll figure out the velocity in the pipe, and then we'll add that into our time of concentration. So looking at this, I've got it listed out as time of concentration for our developed area. Grass is 0.24. In this one I used 50. The precipitation was 4.2, so my time is 0.16. We have paved, there's 372 feet. It is a slope of is actually 2% slope, and its velocity, it says at 0.04 hours. That's not really a whole lot. So when I add that to my overland, we're not getting a lot. So again, and we look at the velocity in the pipe, and it's only got 0.02 hours. So the total time of concentration for post-development is 0.21. Remember, in pre-development is 0.54. Now, each project is going to be a little bit different. Time of concentration for each one of these individual basins is going to be different. Okay? But for the overall design, we're using the largest one to this inlet here for the time of concentration to design our pond by. All right, I'm going to pause here, and then we're going to talk about the runoff, the graphical peak discharge method for post-development.